Let me start with a basic introduction. Before going into this presentation, my humble request is please keep your microphones in mute and don't expect organizers to mute your microphone. Accidentally you might switch on. And also I request all people to pin this screen of presentation in case someone else is presenting. This might not disturb your attention towards the screen. So if you have any questions or doubts in between my presentation, I request you to kindly type this in chat and submit it, such that at the end we will be addressing this questions and doubts one by one, that too sequentially. So moving ahead, I will give you a brief note. So there will be no background disturbances on the slides. There will be no transition between slides. So it will not be like a typical business PowerPoint, and there will be only focus on the content. And also I have to give you a highlight that this is a webinar session. I am not going to teach CFD. That's the prior thing I want to declare here. So the session is going to focus on what is CFD, and then what are the application, what is the process of CFD, and how to learn by themselves. So why I have especially chosen this particular way is, once I wanted to learn something from my professor, that's my PhD advisor. He just gave me only one sentence: rather than giving you fish, I will be teaching you how to fish. Which means rather than giving you food, I will be telling you how to make food or how to get food. So this will make me independent researcher or independent learner. So in that way, what I have done is I have taken several batches over years and tested this method, like give them methodology, learn them, make them to learn, and then come back and tell me a feedback whether you have learned. So I will be checking them by based on assigning some task, say do this problem or that problem, show me in results as a post-processing content or something like that, such that I will be able to have a feedback that this method works. So after testing this method, then I started giving sessions, and I am presently training people only by this method rather than giving workshops. So what are the takeaways that you can have during this webinar or from the webinar is to know about basic CFD. If you do not know CFD as a student or faculty, you will have a general idea what is CFD, then what are the applications where you can apply, and then how the CFD process happens, and finally learning aspects of CFD, like how as a beginner can approach CFD and how to become a self-reliant researcher in CFD. So that's the takeaway from this webinar. So before going into our core content, first I have to clear the myths and misconceptions which we have towards CFD. So some people say that CFD is a subject, and some people give feedback after crediting this subject that is very hard to understand, and it's very difficult to express in examinations, tough to score, and if you choose CFD for projects, it will be time consuming. Also, if you do simulations in CFD, it is time consuming. And there are some people who say that it is applicable for structural analysis, or structural analysis can be done using CFD, and so on. So there are a lot of myths and misconceptions about CFD. Hope this webinar will clear you about all these aspects. So moving forward, first we will start with what is CFD. So CFD is simply said as computational fluid dynamics. So I will give you a different flavor here. So computational is the math part of the CFD, wherein you have to use the mathematics to calculate some of the fluid flow phenomena. So fluid dynamics is speaking about the motion of matter. The matter here which we are considering is about the fluid. So the fluid dynamics is resolved by mathematics, or we are using mathematics to solve fluid dynamics. So simply this 3M, math, matter, motion. If you know all these three, you will be good enough to move ahead in learning CFD. That's what this outline of CFD says. So moving ahead, we have a question: is CFD really a subject? If you ask me in the first hand, I will say no. So persistently, if you ask, I might say yes. So if you firmly ask whether this is really subject or not, I have a different answer. So we will move ahead and see what is that answer. So to study fluid dynamics or any engineering system, we have various methods. So I have listed down some here. So most probably used methods. So analytical method, experimental method, or computational method. So coming to analytical method, what we used to do is we used to have formulas or basic algebraic equations, and we do calculation, that is most probably hand done calculations, and we come up with some approximate solutions most of the time. So if you think about applying analytical solutions for industry grade problems or highly complex 3D problems, it might not be feasible. So people move ahead with another aspect or another method of studying fluid dynamics, that's the experimental method, wherein you can have a probe or experimentally say performing devices or measurement equipments. You can introduce that equipment in the fluid flow, or non-invasive method, you can keep it outside and you can start inferring about the fluid flow phenomenon. So for example, if you take a pitot static tube, which we mostly use in measuring stagnation pressure and static pressure to calculate velocity, it is an in situ measurement wherein you have to stick this probe into the flow, and then you have to take in the value from the manometer or a digital manometer. In terms of electronic displays, you might be having the values, and then you'll be inferring that this is the velocity at this particular point. Suppose if you think about non-in situ measurements, you have a particle image velocimetry or laser Doppler anemometry, wherein from externally you shine laser, internally the particles which are moving in the flow or along the flow will give some scattering. You capture that in camera and post-process that data and infer what is the velocity on a particular plane. So that's how experimental methods say help us to study fluid dynamics. The most recent method is the computational aspect, wherein we will be doing simulations for the above said fluid dynamic problems with a lot of assumptions, governing equations, boundary condition, initial conditions, so on, and we will infer about the physics or what is happening inside that particular equipment or a particular gas turbine engine or wherever the fluid flow is happening. So this aspect is what we are going to deal for this webinar, and you might have seen what is the symbol I have used here. So this is typically a tool that can be used for studying fluid flow. That's how I will represent the simulation aspect. So all the three methods are tools to study fluid dynamics. For experimental method, if you see, you will find hot wire anemometry or particle image velocimetry as a tool. Here in computational fluid dynamics, you have that as a tool to perform simulations. In CFD, there are other aspects wherein you might find different levels of resolution that we will deal little later. So moving forward, the other question which comes to our mind as a beginner, do we all know CFD or not? My answer is partially yes and partially no. If you ask why I am saying partially yes or partially no, is already we have learned fluid dynamics and already we have learned mathematics in your curriculum. Especially if you see partial differential equations, we might have learned integral, differential, and then Taylor series, Fourier series, transformations, and then in the advanced curriculum we might have learned numerical methods. So these aspects already we have learned. If you see computational fluid dynamics, these are the basic ingredients of computational fluid dynamics. That's why I am saying partially yes. So then comes your question, what is partially no? So if you see the answer partially no, it is about integrating this fluid dynamics and mathematics in terms of a program or a software. That's where we do not have a hand or upper hand. So what we can do is we have to give some importance to that particular aspect. If we know that aspect, we will be able to use numerical methods to solve fluid dynamic problems. So we will see each and individual ingredient of this computational fluid dynamics and what are the basic ingredients within that particular ingredient. So if you consider fluid dynamics, there are conservation laws which you need to know, because those are the laws which govern the fluid flow phenomenon. So we might have known from the Reynolds transport theorem, these conservation laws are applicable to a system that can be converted to a control volume, and then These control volume based conservation laws yield governing equations that can be applied for a control volume. So you know how to derive governing equations for a control volume approach, and most of the time we will be dealing with volume based approach for fluid dynamics. We will know why we are doing that in the subsequent slides. Also, we need to know about underlying physics of this particular concept. If we are thinking about conservation of mass, we have to know about the basic definition, what is the governing equation, what does it physically signify, and how does this can be applied to a fluid flow problem. For example, my professor used to give an example for conservation of mass. Conservation of mass, most people know the definition, mass can neither be created nor be destroyed, but it can be transformed from one form to another form. So if you ask about governing equations, dou rho by dou t, del dot rho u equals 0, something like that, directly we will say this is the governing equation. What is the underlying physics? If you take a control volume, the net mass flux is always constant, or you can say whatever is going in through the control volume is going to come out of the control volume. That's how you can understand the physics. For application, here the professor who taught me fluid mechanics, he gave a typical funny application wherein you consider a room, you allow 4 buffaloes to come in and 4 buffaloes to go out. Net number of buffaloes inside the room will be 0, something like that. He gave an analogy. That's where we could understand what is that particular physics and its application. So typical engineering applications, if you see, if you take a pipe, whatever mass of fluid that you are pumping into that pipe should come out of that pipe. That's how you have to see the physics. So this aspect will tell you what are the fluid dynamic portions that we need to consider before venturing into computational fluid dynamics. So moving ahead, we have to think about mathematical aspects, because this is another ingredient which forms a major part in computational fluid dynamics. So why I have given 3 particular topics here is, if you see the first part, partial differential equations. Most of our fluid dynamic phenomena have conservation laws, and its governing equations are in partial differential form. And especially if you see momentum equation, it will have nonlinear term like advective term or convective term. So really we need to know about partial differential equations. That's why I have mentioned this in the first point. The second point why I have mentioned Taylor series approximation or Fourier series approximation is, if you want to convert this partial differential form into linear algebraic form, you need to know the second part. So that's where we need to have a flavor of this series approximations. Then comes the last part. Why I am emphasizing on the matrix part or system of equation is like, suppose if you have multiple linear equations, it will be forming a set of system of equations wherein you can use matrix methods to solve those system of equations easily. So that's where the system of equations part from mathematics and matrix part from the mathematics will help us in learning computational fluid dynamics. Apart from this, there are a lot of small aspects that we can take care, but these are the major aspects from mathematics which we need to give more importance. The last part is about the computer science as an ingredient. So most people from mechanical background, we have a basic course in the initial stage wherein we learn about introduction to computer science or computer programming or something like that. So we have a basic flavor of what computer science does for engineering. So why we need to give importance is like, if you want to use numerical methods to solve governing equations, you have to do it manually by using calculators. For example, a 3 by 3 matrix, if you want to solve, you will be able to use that using a simple calculator, and you can come up with the solutions for these 9 points. Suppose you have a bigger matrix, maybe the matrix is 81 cross 81 or 256 cross 256 and so on. If the matrix is becoming bigger and bigger, larger and larger based on how many number of cell points you assume, or how many number of equations you have. Based on all these aspects, you will have a number of equations. So you have larger matrices to be solved. So taking a calculator and solving these larger matrices is a tedious task. So that's why using computers to solve these larger matrices will be easier for us to go ahead with solving computational fluid dynamics problems. So for that, if you know how to do basic programming for solving matrices, I think that will be helpful. If you do not know in depth to do programming, I think there are tools like MATLAB, GNU, Octave, and so on, which can help you with solving these matrices by simple keywords. So if you call by mat A, you can enter what is mat A and then mat B, and you can use solving methodology by just invoking the commands from the tools which you use. If you are using a tool like MATLAB, Scilab, or Octave, one way you will be able to learn it easily. But if your problem is becoming bigger and bigger, means larger and larger, complex problems cannot be solved using these kinds of tools. Why is like your software will be consuming RAM to the fullest level. So why CFD people do not prefer these tools is this main reason. And I think most people go with Fortran or C or C++. Most people do with Fortran and C. So if you go for machine level languages, I think that will be most appropriate for programming in CFD. So there comes another aspect which is like algorithm. Why we need an algorithm is like you want to efficiently run the programs and efficiently solve the matrices. That's where you have to have a flavor of algorithms. Then the next aspect is graphical aspect. Why we need to think about graphical aspect is mostly what we do is we do all mathematical calculations and we come up with so many number of values, that is numbers. And these numbers, if you have in large clusters, that doesn't make any sense for human being to understand it. So if you have to make a human to understand that, you have to use some kind of representation where people can see and understand. That's where this graphical aspects comes into picture, like converting a number into a color code wherein you will be able to see the color and you can infer some physics out of it. So that's where graphical aspects are important. And last point is message passing interface. This is slightly an advanced topic. Why we need to give importance to this MPI is, suppose if you are purchasing a mobile, you might be seeing a spec wherein people will be saying like this has a 6-core processor, octa-core processor, something like that. Why you have multiple number of processor is you can break down the job into smaller chunks and you can dedicate it to individual processors. Like if you are assigned with a big task, you might be sharing with your colleagues and friends to do that. So you have to know if we want to progress that work in an equal way or equal pace, to say exactly. You have to have some interaction between you, that is as a group of people working for a same project. You have to have communication among yourself. So in terms of processors, if you want to introduce communication, there should be a platform which can introduce communication between the processes. That's where this message passing interface comes into picture. So this message passing interface will say that, okay, I have a small domain. This has this boundary condition. Okay, you have your domain, you have this boundary condition, you solve. So once first iteration is done, the processors will communicate among themselves that we are done with the first iteration. Shall we go ahead with the second iteration? Okay, then all processors will go ahead with second iteration. That's how this message passing interface helps. So most of the softwares it has inbuilt. Suppose if you want to start as a programmer, you have to go for learning this message passing interface. And I think it can be done at the later stage because you will be developing your code for a simple single core processing. Then if your problem is becoming bigger and bigger, then you will be going for parallel processing. That's where this MPI is useful. Moving ahead. So here comes the real part where I'm going to describe about the process of CFD. So most of people might know by using some softwares. People who do not have an introduction, they can have a flavor. Like we have three main parts of CFD. One is about pre-processing. and solving and post-processing. So what does pre-processing do? For doing a computational fluid dynamics simulation, we need to first fix a problem. So we might be thinking about what the problem is. So the problem can be an internal flow problem or external flow problem, or it can be a combustion based problem or anything. So if you have a problem, you have to first bring that problem into your system. So if you want to bring the problem into your system, for example, I will take a simplest problem. I want to study flow over a bike. So if I want to study flow over a bike, I have to bring the bike into the system. So what I can do is I cannot take the physical bike into the system. So what I can do, I can go for a CAD package, I can design a bike there, or I can go for a 3D scanning. I can take original bike, scan it completely, take the surface data, and then stitch it, make a stereolithography file, and then bring it into the system, and then I can start solving. So this aspect, the first aspect is geometric creation. So the mechanical geometry or physical geometry which we are seeing or which we are going to solve, we have to bring it to the system. That's where your CAD package helps. So once you bring in this CAD geometry, next is you have to know what is the flow field about, whether the flow is going through the geometry or above the geometry. For example, if you have to study flow through a pipe, this is an internal flow where the flow is moving inside the pipe, so it will be an internal aspect. Suppose if you want to study flow over an automobile, this is an external flow aspect, so you have to study a flow around that object. So based on this, now if it is an internal flow, now you have to create an internal domain within the given pipe, and then you have to go ahead with further process. Suppose if you want to do an external study, what you have to do is you have to create an external domain like a wind tunnel test section, wherein you can place this object of study, that is a bike or car or airplane or something, maybe a building. So whatever you want, you can have that inside your domain. That is, you are creating an external domain and you are placing this object of study inside the domain. Once this is done, then there is a fluid flow region, whether it is an internal flow or external flow, there is a fluid flow region, that is the domain which can be filled with fluid. So this fluid flow region has to be split into smaller chunks or smaller volumes, wherein you can solve your governing differential equations, that is the PDEs, you can solve there, and then you can have the physical properties. So this division of the fluid domain into smaller chunks is called grid generation. We will be seeing all these aspects in subsequent slides. So before that, there are a few more points need to be addressed. You have to solve a PDE means you have to have some boundary conditions and initial conditions. So you have to define those things in the pre-processing section itself. So this whole pre-processing phenomenon can be done using a part of the software called preprocessor. So once this complete pre-processing is done means you will be having an output file wherein you have a grid or divided domain with supply of boundary conditions, initial conditions. You have to fix what kind of physics you want to solve. Therein you will be deciding what kind of governing equations, that is choosing of governing equations should be done. So once that is done, then you have to go for the solving part. You have to tell your solver, that is the computer program and the algorithms which you have, that you have to start your iteration at this particular level by initializing that process, and then you have to run till this particular part and you have to stop it here, and then you have to save the physical properties or physical quantities into a particular Excel format or CSV format, something like that. So once the data is saved, your solver part is done. This saved data is like a big cluster of data which needs to be made into a human understandable form. That's where this post-processing part, that is the third part, comes in picture. So post-processing tools are either inbuilt tools in CFD software or separate tools available in internet. For example, I can give some of the tool names in later slides. So these tools, what it does exactly is it takes this physical quantity data and the coordinate, geometrical coordinate, this is the position, and this physical property, it coordinates with this, and then substitutes a color with the form of a legend. You will be having a colorful domain and now you do some view manipulation techniques or something like that, and you see how a colorful phenomenon is happening inside that particular domain or around the object. This will allow you to understand what is the flow field is about, what the flow is saying, what is the physics of that particular flow. So all these aspects are seen in post-processing part. So people who are skilled in art, they will be well with this pre-processing and post-processing part, because pre-processing needs art and post-processing also needs some art. So you have to have imaginary aspects that will be able to help you to bring in your best outputs from computational fluid dynamic simulations. So solving is most probably done by this software or tool or code which you use, and you need to have hands-on experience to be efficient with the solver. That's the three part of CFD. Moving further to know about the details. So first part is about the object of study. So the object of study, if you see, you will be able to find this particular aspect. I have given typical examples. This slide, if you see, you might be seeing an airplane, three views of bike, a particular building, a windmill, a car, and then you have a rowboat. So each object has its own dynamics. So why I have placed this particular slide like this is, it will tell you a particular meaning. So the meaning here is, for example, you have this particular airplane. It is completely external flow. So it is an high pressurized environment. So if you have another aspect, I think this bike, this is again external flow, but it is restricted with ground. And then you have this building thing, and building is also this one. This is also a ground-based object, but there is an external flow. And if you see windmill, again you have a ground and you have external flow over the windmill, and you have to note that this windmill have this blades which will be rotating, so it introduces some complexity. So that is one part. And there is one particular part which you can note. This is this particular aspect. Sorry for this previous slide. I think, yes, this particular part, you have this robot. If you see this robot, this condition of this object is partially it will be floating in water and partially will be exposed to air. So this kinds of problem are really tougher for CFD people, which introduce multi-phase flows into this particular process, wherein you have to take in fluid domain, you have to take in air domain, you have to have a solid part. So it's really tough. You have multiple more equations to solve these kinds of problems. But these are really interesting. You can have a wave phenomenon predicted based on wave, what is the feedback given to the robot, how this moves over that wave, something like that. So this is really interesting in CFD, that it can solve any fluid dynamic problem. So coming to domain or grid generation in the pre-processing part, I have given two examples here. One is IC engine, which shows the combustion chamber exactly. You can see the blue color is piston on the bottom side, and you can have the red color. This is for denoting the cylinder head, wherein a spark plug will be located. And you see the green color, that's the sleeve of that cylinder. And within this domain only, there will be the fluid flow, where you will be injecting mass of air, and then you will be injecting fuel, and then you will be giving a heat source, that is a spark, and the combustion phenomenon happens and this piston moves. This is a dynamic problem. The mesh is inside this particular domain, and this is an internal flow problem. And on the right side, if you see, there is a race bike. It is a R1 Yamaha, a typical race bike with 1000cc engine. And if you want to study flow over this particular bike, you have to create an external domain. That's where you see that there is a floor over which the bike is stationed, and you see an external big box kind of wall, and that is an external domain's one particular wall on the rear side of that bike, on the background. So similarly, you have on the foreground, on the right and the left, such that the bike is sitting inside a cuboid. So you see that there are a number of small elements that is on the surfaces you might be able to see. These are all the grids. Or the domain what I have done is internally I have removed the cells such that you will be able to see the cells or the cell sizes based on the surfaces. So the catch here is the bike, if you see the cell size is very small, that is very fine cells, which means this is the object or the point of importance. If you see on the background, you might be finding big elements, that is big squares. It is like as you move away from the geometry, those parts are not important for us to consider. That's where you have bigger size elements. So basic physical aspects of this, I think you will be able to understand why we need this kind of cell or cell sizes for different places. So based on the requirements, you will be able to decide where to give small cell and where to give bigger cell. Moving ahead, you have a boundary condition and initial conditions. For example, if you take this bike, flow over a bike, I have an inlet from the left side wherein the flow can move inside, and for the outlet on the right side where the flow can leave the domain, and there is a wall on the ground side that will be acting as a road, and there is a wall on the bike, that is the bike surface is completely treated as wall. So this wall boundary condition is a particular thing which you are defining in CFD. So it has a mathematical background where V is defined as 0 meter per second. So if I am saying about a boundary condition like wall boundary condition, it is like V equals 0. So there are other boundary conditions like outlet. I have given an example called zero gradient boundary condition. So the zero gradient boundary condition is typically if you have a boundary surface wherein the internal side and external side, if it is of a typical same value, it is called zero gradient. For example, pressure is 100 Pascal on the internal surface, on also external surface it is 100 Pascal, means 100 minus 100 is 0. That's where you have zero gradient. So that's how it is defined. So the other aspect of this boundary condition is I am checking in another system, it is showing. I think you have to pin that PPT. So just check my name, KANNAN BT, you will be finding my name. Other than the video part, you can pin that, so you can be seeing this presentation. I think going ahead with, boundary conditions. There is a velocity boundary condition which I have mentioned. So velocity boundary condition is 10 meter per second. 10 meter per second actually it's an initial condition. So velocity boundary condition, if we are defining, we have to define a profile. If we are keeping this bike inside a wind tunnel kind of situation, wherein the profile will be laminar, or we can say uniform profile. Suppose if you want to test for a road based condition, there will be an atmospheric boundary layer, because atmospheric flows are different. It will have a boundary layer and it will have its own equation. So you have to invoke that equation, that will become a boundary condition. And if you give this initial condition of 10 meter per second, your system will be perfect. If you have all the boundary conditions and initial conditions, you will be able to move ahead to solve your system. Moving ahead, we have to decide what are the governing equations we have to solve. So there are basic governing equations like for a fluid flow problem, we speak always about conservation of mass, conservation of momentum, sometimes conservation of energy. So restricting ourselves to fluid flow alone, if we are not treating about thermodynamic aspects or heat transfer aspects, we can always neglect energy equation and other equations, such that we will be focusing only on the momentum equation. So we will not deal mostly with continuity equation, because continuity is to check the mass conservation, and the momentum equation you have this parameter velocity, that is a physical property which we are tracking, such that this velocity value is simulated by using computational fluid dynamics. So most probably we will be dealing with momentum equation. In later slides we will be seeing how to understand that. So most of the applications or softwares, we will be seeing about Rand's equations. So most of the flow phenomena are turbulent in nature. That's where we will be using Reynolds average Navier-Stokes equation. It is a slightly advanced version of basic Navier-Stokes equation which we are dealing in our basic fluid dynamics. So it's like averaging the equation for some time, say rearranging, we get some closure, and then we have additional equations. That's where turbulence models comes in picture. So these are the basic governing equations which we will be able to use it for solving fluid dynamic problem. If it is a laminar flow problem, we will be solving just Navier-Stokes equations. Also, the steady state or transient, this will be based on what kind of terms we include or what kind of terms we neglect from the system of equations. So coming to solving part, we have to have this governing equations decided, and then once we have that initial conditions, boundary conditions, we have to initialize the system, that telling the system that you have to start your simulation at this particular point and end at this particular point. And also you have to monitor your residuals. What is the residuals mean? If you are doing a numerical iterative process, the iteration as it proceeds from one level to another level, it will have a difference in solutions. So finding the differences and plotting in a logarithmic format, it will tell you whether your solutions are approaching towards the exact solutions or not. So in CFD we are typically solving partial differential equations using iterative methods. So that's where we have a requirement of tracking this residuals. So the right side picture, if you see, you have a legend on the right top corner. So this part, it will say that what are the equations I am solving. So ux and uy, it says that it is a two-dimensional problem. If it is three-dimensional, it will be ux, uy, uz. And there is a pressure and then epsilon and k. So the equations are like Rand's equations in 2 dimensions, pressure Poisson equation, then k epsilon equations that are separate equations. So these equations are solved and the residuals are plotted with respect to iterations. How many iterations I am doing and what is the residual level. So there is a next part called convergence. So this convergence is a requirement wherein you have to bring the solutions to an exact level and you have to stop your solver, so that is a simulation, and then you have to save your result. So to reach this convergence, you have to set the residual levels. So if you see this y-axis, there will be different levels from 1 to 10 power minus 5, minus 6, minus 7, something like that. So how to know that whether our solutions is converged or not? The solution convergence is based upon what kind of level you fix for your solver. So suppose if I am going for an internal flow problem, I might fix my residual level at 10 power minus 6. So if these lines are going towards 10 power minus 6, our system might say that okay, we have reached this level, and the system will stop the solver, and you can save your results. Suppose if this graphs are not going down, rather it is going upwards, which means that you are deviating from your original solution and your system is going unstable. There are stability issues. So you have to go back and check your other conditions which you are given. Maybe a mesh problem, maybe an initial condition problem, or boundary condition problem. Wrong choice of inputs if you have taken, this will not go down. That is, the graphs will not go down, it might go up. So once you satisfactorily come to a conclusion that your solutions have converged, then the next part is you have to save your solutions. So saving your solutions, you have to do it then and there, such that if there is a power shutdown or there is any technical glitch, you will have always a backup from where you can start your simulation, and again you can reach your convergence. So that's where your saving solutions is a mandatory process. So we have seen solving. Then coming to post-processing, this is the most important process of CFD, wherein you have all the governing equations solved at each and individual elemental volumes present inside the domain, and you have all the physical property values like velocity, pressure, temperature, density, whatever you have considered. So you have all this in individual cells like x, y, z. This is a coordinate point in the domain. I have this velocity value, I have this pressure value, I have temperature value, I have kinetic energy value, something like that. So this value doesn't make sense. That's where we have to convert these values to visuals. That's the particular term I use here. Values to visuals is exactly called post-processing. So you can use any post-processing tool to convert the numbers into visual process. So if you see the header above post-processing, you might be seeing a small rectangular domain. The flow is from right to left. So that's how this flow is given. So this particular box, that is the rectangular box, is moving from left to right, or you can treat it like flow is moving from right to left. You have a flow which is moving above that particular box, that is shown in red color, which means acceleration of fluid. So this color says that it is of higher velocity. You see that legend shown below this post-processing. This is the U magnitude. Red color stands for 50 meter per second, which means this has an acceleration process there. And you see some blue color over the domain, that is on the rear part and the frontal part. So this is about the recirculation zone or the wake zone behind the domain. This is on this part, this side. And on the frontal side, it is partially stagnating and partially recirculating. So this is in a smaller aspect because those molecules are stagnant and it is subjected to some forces based on the motion of that particular box. So that's how this inference can be made. And if you see a below picture, this is the bike. I have plotted streamlines on a horizontal plane. How to plot streamlines is like you have to take the velocity values and then convert it into a streamline, and wherever you want in your domain you have to select injection points and then allow the streamline to move through that point. So once you have given this based on your forward integration and backward integration based on your post-processor, the molecules start moving based on the flow field data, that is velocity data. With all the XYZ points, you will be able to draw this streamline. So once you have this, now you can see this domain. It will show you that there is a recirculation zone just behind the bike, and these streamlines on the upper side are being pushed towards the suction zone or the wake zone. So streamline pattern itself will say how the flow field is moving behind the wake. Now if you have a silencer and if you allow this smoke to move out of that silencer, how does this mix with the fluid flow on the rear side? So people who are working on road-based authorities, they can decide about what is the minimum distance between one vehicle to another vehicle such that this exhaust doesn't come as an fluid flow in front of your face that you can inhale. So to avoid that, there will be minimum requirements. These regulations are based on these kinds of simulations which we are doing. So the other aspect is shown on the bottom side. It's like a transient flow field wherein I have done some post-processing called Q criterion. So it's a derived post-processing wherein I created an utility in C++ and then I have derived that. So how I derived that is I took a velocity flow field and based on manipulations, that is mathematically I manipulate the velocity data to calculate velocity gradient tensor, and from velocity gradient tensor you can have the derivatives invariance, and one of such invariance is taken and an ISO value of that is stitched into a contour, and you are seeing those blobs. These are exactly showing the vortices or vertical structures or rotating mass of fluid elements. So this will have crazy structures. On seeing this, you will be able to understand how this structure or how much amount of fluid is rotating in what direction, what magnitude. So you can superimpose velocity magnitude. If you see on the right side, I have a superimposed velocity magnitude over vorticity. So you can do all manipulations which you want to do, and you can make your solutions as attractive as possible. That's the beauty of CFD. On seeing this slide, you might be finding that CFD as a colorful fluid dynamics. I agree partially with that. Colorful fluid dynamics is one aspect where your CFD results will be always attractive to the people who see your results. Also, there is another way to see the same CFD. It's contentful fluid dynamics, which means each and every picture will have its own content. So it is like you have a simple picture and you have a post-processed picture. It will say about the physics of the fluid flow. So that's where I can say this colorful fluid dynamics goes well with contentful fluid dynamics, which is simply computational fluid dynamics. So based on this, I think I have given an overview of what are the three processes in CFD. So moving further, now you might ask me a question: what are the applications that can be solved using CFD? So for the applications, you might think based on the objects which I have shown, there are multiple applications. Any fluid flow phenomenon, if it has a governing equation and a physics behind it, you will be able to solve using CFD. That's the best part you can have in CFD. The main part of this webinar comes in the learning aspect. So we have 10 to 15 minutes ahead. So I will go ahead how to process or how to see how you can learn CFD. The first aspect is before moving towards the CFD, I will ask you to go ahead with fluid dynamics, wherein you can go for reference books, standard books, or NPTEL lectures, or EDX lectures, or Coursera, whatever you want. Be thorough with the fluid dynamic aspects. So the other aspect to learn fluid dynamics is like you can go for reference literature. In-depth physical phenomena can be understood by that way. So the latest literature will help you in knowing about the latest phenomena, such that might be useful in your research or your learning process. So I use a typical method wherein blog about fluid flow daily in Quora, and a few people subscribe to that. They ask me questions and we interact on daily basis, such that this enables them to learn smaller aspects of fluid dynamics in smaller materials. The second part is about mathematics. Whatever you have learned in your curriculum is fine, and you have to revisit it, and then you have to take whatever portion I have told, like partial differential equation, Fourier series, or Taylor series, or this part like algorithms, so solving aspects, and how to solve this set of governing equations or linear equations using matrices. All those things you can refer to standard textbooks or videos, and you can find tips and tricks how to solve this easily from internet. I think you will be able to learn that. So once you have the strong foundation of fluid dynamics and mathematics, you can go for computer science aspects. I will not suggest you to go for programming language directly. If you already know something, you can try with basic examples like recipes for C, recipes for Python, something like that. It's available online. You'll be able to use that sample template code, and you will be able to program your own thing. And there are a lot of softwares, tools, or typical codes compiled together are available online. So you will be able to use that, and I think from that aspect also you can learn. The other aspect is most of the time there are thumb rules available in using softwares or codes. So you have to search blogs or forums to find what are those thumb rules. Some people say that you initialize at 0, some people say initialize at 100, and then move ahead with the solution steering, something like that. These are all thumb rules purely based on experience. You might be having these thumb rules. So please go ahead and find that from internet. There are three typical methods in CFD. This is finite difference method, element method, and volume method. Finite difference method is basically in a very elementary form. You will be converting partial differential equations or terms in that into algebraic forms, and then solving that. And finite element method is somewhat out of league, and there are people who use this for fluid flow, but it is essentially made for solving structural mechanics problems. That's why I do not encourage people. But if you still want to try, you can try this, and I think it will be giving you more error. You have to work hard to get a perfect solution. And the best method is finite volume method. You will be seeing in all the softwares or almost all the codes. So that's where finite volume method is the best method that you can use for say learning CFD. Why finite volume method? If you ask me codes, is this basically all tools are using finite volume method. The other aspect, the most important aspect, is the intuitive approach. Like whatever equation you see, it will be meaningful, you will be able to understand it, and you will be able to apply this for complex problems and complex physics. So how to learn finite volume method? I will suggest you two books like Numerical Heat Transfer and Fluid Flow. It's a perfect recipe for learning numerical methods for solving fluid dynamic problems by Suhas V. Patangar. This is the very fundamental 70 to 100 page book, very small book. You will be able to learn by yourself. Or if you want a story type approach or a very lenient, subtle way, you will be suggested with Introduction to CFD Finite Volume Method by Westig and Malal Segra. I follow these two books for learning and teaching. So I think you can also go ahead with these books. How to learn? So before going into finite volume method, we have to give an approach. Your book, which I have referred earlier, will be going in this particular order. First, we have to learn general transport equation, then finite volume method for diffusion, advection, and then about other aspects like time discretization and other algorithms. So why this particular way? If you see this general transport equation, this is very simple partial differential equation. If you understand this one equation, you will be able to understand all the governing equations in fluid flow, and you will be able to come up with your own equation for your new physics also. So this equation has 4 terms. The first one is this temporal term, wherein you will find rate of change of the property phi with respect inside a particular volume. Rate of change of phi inside a particular volume. That is the control volume which we consider. The second aspect or the second part is advective derivative, which means that the rate of change of property phi when the fluid is moving from one point to another point in a domain. This is the spatial aspect is considered in the advective or convective derivative. This is what this divergence of phi is telling about. The right hand side, if you see diffusion term, it speaks about how phi diffuses with respect to space. And the last term is about the source. So any source if you have which can influence this advective and diffusive phenomenon, that can be included to source term. It can be a temperature source, it can be a heat source, it can be a pressure source, and whatever it can be. So now if you see this equation, if you take phi and if you substitute it with 1, you will be coming up with an equation like dou rho by dou t, divergence of rho v equals 0, which is a conservation equation for mass, continuity equation. If you substitute phi with u, you will be coming up with the momentum equation. So dou rho u by dou t, it's a temporal derivative. Then u divergence of v, this is again advective derivative, and this becomes a total derivative. On the right side, gradient of u, wherein you can remove this gamma and you can replace it with viscosity. You will have divergence of mu grad v. It becomes a viscous resistance or viscous term or viscous stress term. On right side corner element, you have this s phi. This is a source term wherein you can have gravitational term or dou phi by dou x. That's a pressure gradient term or electromagnetic or magnetohydrodynamic term, or whatever term you want you can have. So I will give more importance to this equation. You please understand this equation and you try to derive your governing equations from this. So this is what the book essentially deals with. So each and every term in this equation is a chapter for that book. Coming to especially diffusion part, why we have to give diffusion so much importance? It's like diffusion is an individual phenomenon or independent phenomenon. If you consider a room, if you don't give any energy, you just switch off the fans, you do not have any disturbance and leave it as such for a hour or so, the molecules will not be idle. It will be moving here and there based on random molecular motion. This is what exactly the diffusion process is based on. So if you take a perfume inside that particular room and keep it in a corner, from one corner to another corner, the perfume to spread, it will take 15 to 30 minutes. if there is no fan or no motion of air in bulk. So it is a molecular level phenomenon that can happen very slowly with respect to time. If you want to have a typical example, I have given a physical example of perfume in a room, and for heat transfer aspects you can have a conduction equation wherein you can have an element, you give heat source on one side, it will be transferred from one molecule to another molecule, and this can be treated as a diffusion problem. So in finite volume method for diffusion, what it does is exactly you might be treating a one-dimensional element, and say this is a one-dimensional thing, and you choose a single point, then you might choose adjacent points on two sides. This might be an eastern side point, this might be an western side point. This is the point of consideration. And then what you will be doing is essentially you might be treating about the surface fluxes at the walls of this particular central element. So the flux from the right side surface minus the flux from left side surface will be exactly the net flux for the element considered in the center. And similarly you will be doing this process, and you will be coming up with equation for this phi, and those are all linear equations if you do this process. And this linear set of equations can be converted to matrices, and if you solve, you'll be able to get a solution for this diffusion problem. This is in one dimension aspect I have shown. This can be done in two dimensional aspects, wherein I can say bring in points like north, south, and then front and back for 3 dimensions, something like that. So you give importance for a one-dimensional problem, learn it, then you can extend it to two-dimensional problem and three-dimensional problem, and so on. So this is what is about learning finite volume method for diffusion. Finite volume method for advection. So why advection is like, advection is a bulk motion, like you have the same room example, you will switch on the fan and it is creating bulk motion to happen, wherein the already diffusion is already happening, which is inherent. You introduce a basic perfume in a corner of the room, now switch on the fan, within 2 minutes or less than a minute, you will be able to have the smell of the perfume. That's where the advection phenomenon is happening. And now, rather than diffusion, you will be seeing the fluid flow phenomenon happening here. So the advection term is really say introducing the fluid flow, and if you do same this finite volume method operation, you will be able to solve fluid flow of problems in 1 dimension, 2 dimension, and 3 dimension, and so on. And moving further, we have this temporal derivatives wherein time at this instant, previous instant, and next instant. There are simpler methods. If you understand this diffusion and advection, these are very straightforward to understand. And the last part is about adding additional governing equations. So this is about if you want to have new physics to be added, like you want to solve combustion problem or heat transfer problem, you can add additional governing equations and you learn about the physics, and then you'll be able to solve that using CFD. So if you ask me how to learn via softwares, there are open source softwares and commercial softwares available. If your college has subscribed or purchased commercial softwares, please go ahead and use that. Only by practice you will be able to learn. If you do not have any commercial softwares, I will suggest you open source softwares. People who are well versed with Linux, you'll be able to download OpenFOAM or SU2 or something like that, and you'll be able to say start practicing. And if you do not have a Linux based system, I think Windows based SimFlow kind of free versions are available, wherein some of our colleagues from other colleges, they have implemented this as a curriculum for CFD laboratory, and they are teaching it. And I had a real feedback from my friend Professor Muthuraman from PMIST that they are using SimFlow because we interacted long back implementing this in our curriculums. And also Professor Rajin from Chandigarh University, he is working on OpenFOAM for CFD teaching or tutoring purposes. So I feel by practice you can go ahead and solve a single one-dimensional problem using these softwares, and then see your finite volume for diffusion or advection problem. In the book, you will be able to correlate one to one, and you will be able to understand the phenomenon or physics behind the flow, and also you will understand how the software works, how you get error, how to rectify it by yourself. So thank you for patiently listening to my talk for a hour or so. and I will be happy to answer questions from your side, and I think you will be able to start learning this computational fluid dynamics by yourself. So going back to the fundamental question, whether it is a subject, it is a tool that can be used to study fluid flow. If you ask me whether it is tough, it is not at all tough. It is only to be understood by people. It is very subtle and very intuitive and very interesting in nature. And the other aspect is it can be used to solve any fluid flow problem. I think I have addressed all the points which I started with the webinar. So I will be sharing this PPT to the organizers, and I think they will be able to share it to you. And I think we will start with the question and answer session. If you have questions, I think moderators, organizers can tell me one by one. I'll be able to answer.